A brief review of the general gas equation. So here we have P1V1 over N1T1 is equal to P2V2 over N2T2. Basically, these two situations set equal to each other as they share the same ideal gas constant. If the number of moles of a gas in an experiment is constant, which is frequently the case, the expression becomes the combined gas law equation. So we notice that we're going to take out number of moles here, because they're equal to each other. So now we're left with P1V1 over T1 is equal to P2V2 over T2. Let's look at an example. If a gas exerts a pressure at 3.1 atmospheres with a volume of 105 milliliters at 25 degrees Celsius, what would the new volume be at STP? Okay, so if I was going to start this, I would say my pressure is 3.1 atmospheres. My volume is 105 milliliters. And I could keep it as that as long as I'm fine with the fact that my answer should also be in milliliters. My temperature is equal to 25 degrees Celsius, and we have to add 273 to that. And when we do that, we find that it is going to be 298 K. And these are all my initial values. So this is P1, V1, and T1. They say here that the new conditions are going to be at STP. So that means my P2, and at STP pressure is 1 atmosphere. We got to stay in the same unit of pressure. We're going to solve for V2. That is going to be my X. And T2 is going to be the temperature at STP, which we know is 273 K. So now I have all my variables except for the one that I'm solving for, which in this case is V2. So if I rewrite my formula, it's P1 V1 over T1 is equal to P2 V2 over T2. Now I'm going to take these variables and I'm going to plug them into my equation. So I'm going to have 3.1 atmospheres. My volume is 105 milliliters. My temperature is going to be 298 K. And that is going to be equal to P2, which is going to be 1 atmosphere, V2, which is what I am solving for, that's a V, and then T2, which is temperature at STP, which is 273. So if I cross multiply and divide and solve for my unknown variable of V2, I find that my V2 is going to be 298 milliliters, which matches what I started with. Or if we were to convert it into liters, it would be 0.298 liters. And if we were to do that to the correct number of significant figures, which is 2 significant figures here, we would have that equal to 0.30 liters. If we went to liters, let's look at another example. An ideal gas, originally at 0.85 atmospheres and 66 degrees Celsius, was allowed to expand until its final volume, pressure, and temperature were 94 milliliters, 0.6 atmospheres, and 45 degrees Celsius, respectively. What was the initial volume? So we're going to write P1 V1 over T1 is equal to P2 V2 over T2. So my initial pressure is 0.85 atmospheres. So my P1 is 0.85 atmospheres. And if you want to list these out ahead of time, that's always a smart move. My V1 is what I am solving for. My T1 is 66 degrees Celsius, so 66 degrees Celsius plus 273, that is going to give me 339 K. So I'm going to put 339 K on the bottom. My P2 is 0.60 atmospheres. My V2 is 94 milliliters. My T2 is going to be 45 degrees Celsius. So 45 degrees Celsius plus 273 is going to equal 318 Kelvin. So I'm going to put that on the bottom. I am solving for V1, so if I cross multiply and divide out, my V1 should be around 70.7 milliliters. And if I do that to two significant figures, which I need to do again, 71 milliliters is my final answer. And that is a brief review of the general gas equation, otherwise known as the combined gas law.